This lesson is all about radioactivity and half-life. So we've already discussed what an isotope is, but as a refresher, it's when you have two atoms of the same element, and that's really important, they have to be the same element, have a different number of neutrons. And because they have a different number of neutrons, they have a different mass. Now again, let's just refresh. In the nucleus of an atom, we have protons and neutrons. They are the same size, and they are the two particles or the two parts of the atom that actually give the atom mass. But it's the number of protons that determines what type of element you are. So carbon-12, which is one isotope of carbon, has 6 protons and 6 neutrons. Carbon-13, however, while it still has the 6 protons, it has 7 neutrons. And carbon-14, again, still has 6 protons because that's why it's carbon, but it has 8 neutrons. It is the addition of these neutrons in the nucleus that actually can cause radioactivity. The way I like to think of it is, imagine you're trying to hold as many basketballs in your arms as you could. At a certain point, there's going to be too many and they're going to start to fall. It's the same thing with the nucleus. The nucleus has a stable form, and the most stable form for carbon happens to be carbon-12. But as it adds more and more neutrons to that nucleus, it starts to become more unstable, and eventually those neutrons or one of those particles is going to fall out of the nucleus. So it's as if the nucleus just can't hold on to it anymore, and eventually part of it has to leave. So radioactive decay is what we call the process when an atom's nucleus does just that, when it releases that particle, and at the same time it also is going to release energy. This is what makes radiation or radioactive elements dangerous, is it's the energy that they release that can cause damage to living organisms. But when this happens, the nucleus of that atom releases a particle, and in doing so, it's actually going to change from one type of element to another. Because again, remember, it's the number of protons that determines what type of element you have. And so when an element undergoes alpha or beta decay, which are the two we are going to discuss, that element actually becomes a brand new element. So let's talk about alpha decay first. Alpha decay is when a radioactive nucleus, which just means a nucleus that is unstable, releases an alpha particle. An alpha particle is 2 protons and 2 neutrons. So this, what we call the parent nucleus, loses 2 protons, creating a daughter nucleus, a nucleus that has lost 2 protons and 2 neutrons. So this was the original nucleus. It pops out an alpha particle and leaves behind the remainder of the nucleus. When this happens, the element changes because our atomic number changes by 2. It goes down 2 because we lost 2 protons. And the atomic mass goes down by 4 because protons and neutrons have the same mass, and we've lost 4 particles total. Okay, so again, just looking at this in terms of how we would do this on the periodic table. Radium has an atomic number of 88. After it undergoes alpha decay, it loses 2 protons. So we take that number 88 and subtract 2 protons. So our atomic number has gone from 88 to 86. That's why it becomes radon. Then if we looked at the mass, it was 226, but because we lose 2 protons and 2 neutrons, so a total of losing 4, 226 minus 4 leaves us with a mass of 222. So the new element that is created is radon 222. Okay, I'm going to walk through this one more time just to make sure it's making sense. We're going to do it with another element. We're going to do it with sigaborium. So sigaborium 263. Now remember we learned in isotope annotation, the way we write an isotope is you write the chemical symbol and then the mass. Now for all of these problems, I will give you the atomic number so that you know where to find it on the periodic table. So sigaborium has an atomic number of 106. After it undergoes alpha decay, what will it become? So let's walk through this. The first thing that we want to do is figure out what's the new atomic number going to be so that we can determine what the new element will be. 106 minus 2 equals 104. I would then look at the periodic table, find number 104, and I would see that it's Rutherfordium. So I have my new element right here. So I know my daughter nucleus is going to be Rutherfordium. Now I need to determine the new atomic mass. I gave you the mass of 263. If it's alpha decay, it lost 2 protons, 2 neutrons. That means it lost a mass of 4. 263 minus 4 is 259. So my new element is Rutherfordium 259. So let's talk about beta decay. Beta decay is a little bit different. In this case, it's when a neutron changes into a proton. So what happens, you remember how neutrons are neutral? Well, when an atom undergoes beta decay, the neutron splits into an electron, what we call a beta particle, and that leaves behind a proton. So the neutron changes into a proton. Again, this is going to change what type of atom we have because we now have one more proton than we did before. So our atomic number goes up by 1. But our mass does not change. And the reason the mass does not change is because electrons are so small, they don't add mass to the atom. So even though an electron is released, the atomic mass stays completely the same. So if I look at this from the periodic table standpoint, polonium, atomic number of 84, undergoes beta decay. 1 neutron becomes a proton. That makes the new atomic number 85. So my daughter nucleus is now astatine. It went from polonium to astatine. However, the mass is not going to change because the neutron becomes a proton, but they have the same amount of mass. So my new element is astatine 218. So the atomic mass stays exactly the same. Okay, one more example. Sodium 24. Atomic number of 11. What will it become after beta decay? Again, first thing you do is determine the new atomic number. 11 plus 1, because 1 neutron became a proton, is 12. So my new element has an atomic number of 12. Look at the periodic table. 12 is magnesium. Determine the new atomic mass. Well, there was no change in mass, so I don't have to do anything. So my new element is magnesium 24. So it went from sodium 24 to magnesium 24. Okay, last little bit. Half-life. So radioactive elements, you can have a sample and they undergo decay, and every element has its own particular half-life, what's called a half-life. A half-life is the time it takes for half of the atoms of a sample to decay, to undergo either alpha or beta decay. So what that means, for instance, is if I had 50 grams of sodium-24, after one half-life, half of that, 25 grams of that, would have undergone beta decay, and I would be left with 25 grams of sodium-24. After another half-life, 12.5 would have undergone decay, and I would be left with 12.5. Now really you can't have a 0.5, but it would be 12 or 13. After another half-life, again, it would be cut in half. So the half-life is how long it takes for half of that sample to decay, to change into something different. So let's go through an example of this. Sodium-24 has a half-life of 15 hours. How many half-lives will it have gone through after 45 hours? So if sodium-24, after 15 hours, half of the sample has undergone beta decay, how many half-lives do I get in 45 hours? So if I have 45 hours, we just got to do a little bit of algebra. I know that my half-life is 15 hours. I know that I have gone a total of 45 hours. So how many half-lives do I have? 45 divided by 15 means I have undergone 3 half-lives. Now, you could probably figure that out if you had just done the addition. Well, 1 half-life is 15 hours, 2 half-lives is 30 hours, 3 half-lives is 45 hours. But doing it with algebra is actually a little bit faster. And with some of the half-lives where they're much larger numbers, using algebra will be incredibly beneficial. Okay, so you're going to see some problems like that. The other type of problem that I'm going to be giving to you is asking you to figure out how much of a sample was left, or how much of a sample did you start with given a specific number of half-lives. So let's look at one of those. If you started with 100 grams of half of the sample, and half of the sample is lost after every half-life, then after 3 half-lives, how much is left? Now, I'm going to show you how to do this algebraically, and then I'll explain the other way in which you can do it. So, if after every half-life 50% of the sample is gone, that means you would take 1/2 to the third, because you have 3 half-lives. So it's a half times a half times a half, or 1/2 to the third, or 1/8 of the 100 gram sample will be left. Okay, so that means you would take 1.25 times 100 grams, which gives 12.5 grams. So after 3 half-lives, there will be 12.5 grams of my 100 gram sample remaining. Another way you could do it is to just do it out. You would say, okay, if you start with 100, after 1 half-life, there would be 50 grams. After a second half-life, there would be 25 grams. After a third half-life, there would be 12.5 grams. And you could also, so you could do it that way as well. It just would take a little bit longer to get through, especially if you have 5 or 6 or 7 half-lives. But that is the other way in which you can do this.